Good day, everyone. Today, we'll be talking about inorganic compounds. But before we begin, let's first define what they are.
That's right. Inorganic compounds are substances that usually do not contain carbon hydrogen bonds. They are different from organic compounds, which are mainly based on carbon.
Examples of inorganic compounds include salts, metals, oxides, acids, and bases. These are the compounds we often encounter in our daily lives, like table salt, water, or even the dioxide we exhale.
Inorganic compounds are very important because they play a big role in the industry, agriculture, and even inside our bodies. For example, fertilizers contain inorganic compounds that help plants grow.
So, in summary, inorganic compounds are essential not only in chemistry but also in our everyday activities and environment. For this segment, we'll talk about metal, non-metal binary compounds, also called ionic compounds.
In naming these compounds, the cation is always written first, followed by the anion. Their charges must balance, so the total is zero.
If the cation is a metal ion with a fixed charge, we simply use the element's name. Common examples are from Group 1A, Group 2A, zinc, aluminum, and silver.
For example, Mg2 positive is a magnesium ion. For aluminum 3 plus, it's an aluminum ion, and so on and so forth.
So, in short, naming cations, just use the element's name if it has a fixed charge.
That's all for our lesson. Thank you for listening.
Earlier, we talked about fixed charge cations. Now let's move on to metals with variable charge, mostly transition metal.
Yes, these metals can form more than one type of ion, so we must show the charge in their names. There are two ways to do this: the stock system, which uses Roman numerals, and the classical system, which uses the suffixes us for the lower charge and ik for the higher charge.
So, for the example number 1, we will be using the Cu positive. As you can see, the Cu positive has a lower charge, which means it is called copper 1 ion in the stock system and cuprous ion in the classical system. We use Us because it has lower charge. Now, for example number 1, for the example number 1, we will be adding Cu positive and Cl negative. Now, before we add first, let's do the crisscross method. In doing the crisscross method, when the element has the same charge of the number, we'll just simply cancel them out, and that will give us CuCl, and the name of it is copper 1 chloride or cuprous chloride. So, for the example number 2, the Cu positive plus the oxygen 2 negative, and after the crisscross method, it will give us Cu2O. And can you guess what name is it? If your answer is copper 1 oxide or cuprous oxide, then you are correct. Take note that you should be doing the crisscross method when adding. Now let's move on for the example number 2. For the example number 2, we will be using the Cu2 positive. And if you saw earlier that Cu2 positive is greater than Cu positive, then the name of it will be copper 2 ion or cupric ion. We will be using the ic when the charge is greater than the other one. For this example, we will be adding Cu2 positive, which is the cupric ion, and the Cl negative, which is the chloride. Then, just like what I've said, that we should be doing the crisscross method, then it will give us CuCl2. And the name of it is copper 2 chloride or cupric chloride. Now, for the other example, we will be adding Cu2 positive and O2 negative. As you can see, 2 and 2 are the same, so we can just cancel them out. And it will give us CuO, which is copper 2 oxide or cupric oxide. Now, let's head on to our last example, which is the example number 3. And for this example, we will be using the Fe2 positive. Can you guess which suffixes we will be using? The us or the ik? If your answer is us, then you are correct because the ik is the Fe3 positive. For this example, we will be adding Fe2 positive, which is the ferrous, and Cl negative, which is the chloride. And just like what I've said, we will be doing the crisscross method. And after the crisscross method, then we'll have the FeCl2, which is iron 2 chloride or ferrous chloride. Now, for the other example, we will be adding Fe2 positive and O2 negative. Now, as you can see, that 2 and 2 are the same. And just like what I've said, if the charges are the same, we will just cancel them out and it will give us FeO, which is iron 2 oxide or ferrous oxide.
So the pattern is simple. Use Roman numerals for the stock system. Use lower charge and ic for the higher charge in the classical system.
Exactly. And by looking at the formula, you can figure out the metal's charge by balancing it with the charge of the anion.
Now, let's proceed to the monatomic ions. Simple rules. Take the English root of the element's name and add "ide."
So every single atom, negative ion, just gets hide, even if the charge is different.
Yes, the name uses only the element root plus the suffix "ide." The actual charge, like 1 negative, 2 negative, 3 negative, is not written in this name for simple anions. Chlorine plus IDE would become chloride even if it has just one atom, negative atom.
Got it. Show me some examples.
Now, for this example, we will be using chlorine. And before we do, let's spot the element root. Can you tell me what is the element root of the word chlorine? If your answer is chlor, then you are correct. Now, we will just add the English root word, which is chlor, plus IDE suffix, then that will give us chloride. Now, for the second example, we will be using sulfur. Now, can you tell me what is the root word for sulfur? If your answer is sulf, then you're correct. And we'll just add IDE for the suffix and it will give us sulfide. Note in spelling. Element is sulfur, but the anion is sulfide, not sulfuride. Many elements change slightly when adding IDE.
For the next example, it's phosphorus. Can you find the root word for phosphorus? If your answer is phos, you are correct. So the root word phos plus ide is equivalent to phosphide. For the next example, I will give you 10 seconds to answer it. If your answer is oxide, then you are correct.
So basically, metals usually form cations, and their names don't use "ide". The "ide" rule applies to anions that are single atoms, non-metals mostly. For example, sodium Na positive is sodium ion, not sodium nide, right?
Yes, you're on the right path. Now that you've mastered it, let's ask the audience too. What are the names of the anions if you put the suffix IDE for these ones? If you answered nitride and fluoride, you are correct.
Okay, we already learned about simple ions with I. Now let's move on to polyatomic ion.
Those are ions made of more than one atom, right?
Exactly. Most polyatomic ions are oxyanions. Oxygen plus another element. Their names usually end in ite or ate.
Let me guess. 8 means fewer oxygens and 8 means more oxygens.
Correct. For example, NO2 negative is nitrite, which has less oxygen, while NO3 negative is nitrate, which has more oxygen.
Oh, and what about when there are more than two?
That's when the prefixes come in. Hypo plus the root word plus I means the least oxygen. And for the highest oxygen, it's per plus the root word plus 8.
Nice. And some exceptions exist, right? Like hydroxide, peroxide, and cyanide.
Exactly. Now let's check 5 examples of compounds with polyatomic ions.
For the first example, KNO2. Now, the polyatomic ion is NO2 negative, which is nitrite, because it has fewer oxygens. Now, in simply naming, we just put the metals, which is potassium, then add the polyatomic, which is nitrite, and the name is potassium nitrite. Now, for the second example, KNO3. The polyatomic ion is NO3 negative, which is nitrate. Same central atom, negative, but more oxygens, which 8. The metal is potassium, which will be coming first, followed by the polyatomic, which is nitrate. And the name will be potassium nitrate.
For the third example, for the third example, the polyatomic ion is SO3 2 negative, which is sulfide. But after the crisscross method, it becomes Na2SO3. And the metal is sodium, which makes it sodium sulfide. So, for examples from Khalid's question, if there are polyatomic ions with more than two oxygen ions, here's the set example. So, for our example, our root word will be chlor since it's mainly chlorine. So, for the first one, ClO negative becomes hypo plus the root word chlor plus the suffix ite. So it becomes hypochlorite. For the second one, ClO2, you just have to add the root word chlor to make it chlorite. And for ClO3, since it's higher than both ClO and ClO2, it gets chlorate. And for the last one, ClO4, since it's higher than all three, it gets the prefix per and the suffix ate to make it perchlorate.
Okay, so the trick is to watch the ending ite, ate, hypo, per, depending on the oxygen count.
Exactly. Once you memorize the common ions, naming their compounds gets easy.
Got it. Next time I see Na2SO4, I'll know it's sodium sulfate, not just sodium something. Okay, now let's talk about naming binary molecular compounds. That's when two nonmetals combine.
Right, that's different from ionic compounds, which are metal plus non-metal.
Exactly. The rules are write the least electronegative element first. Add the suffix "ide" or IDE to the more electronegative element. Use Greek prefixes for like mono, di, tri, tetra, and etc. to show how many atoms are present. But if the first element has only one atom, don't use the prefix mono.
Got it. So we use prefixes not only when needed, and always end the second element with "ide."
Perfect. Let's go through three examples.
So for example 1, we have CO, and carbon comes first since it's less electronegative, and oxygen second with the prefix "ide." Since oxygen has only one atom, we use the prefix mono, which makes carbon monoxide. For example number 2, we have one carbon and two oxygens, which makes carbon since it's the first one, so we don't have to add mono. So it becomes carbon dioxide since there are two oxygens.
Okay, we'll learn how to name anions, polyatomic anions, and molecular compounds. Now let's move to acid.
Right. Acids are a bit different because the name changes depending on whether they're in pure form or dissolved in water.
Exactly. Rule number one. In pure form, hydrogen is just named as hydrogen plus the nonmetal. But when dissolved in water, the acid naming system is used.
And how do we form the acid name?
First, drop the word hydrogen, then add the prefix hydro to the root of the nonmetal, and change the ending of the nonmetal "ide" to "ic", then add the word acid.
So hydrogen chloride becomes hydrochloric acid in water.
Exactly. Let's go through three common examples. For example number one, the HF, which is Pure form of the HF is hydrogen fluoride. Now, when dissolved in water, we take hydro, then the root word fluor, then add ic and acid. Now it's hydrofluoric acid. Change the fluoride to fluoric.
Now, for example number 2, HCl. In pure form, it's called hydrogen chloride, but in water or aqueic acid, it's hydrochloric acid. Add the prefix hydro to the root word chlor. Change the ide in chloride to ic, which makes it chloric, and add acid, making hydrochloric acid.
We already studied binary acid. I wait. We already studied binary acid like hydrochloric acid and hydrosulfuric acid. But what about acids that contain oxygen?
Oh, those are called oxyacids, right?
Exactly. Oxyacids are formed when hydrogen combines with a polyatomic oxyanion. The rule is simple. If the oxyanion ends in ite, the acid ends in OUS acid. If the oxyanion ends in ate, the acid ends in ic acid.
So, no hydro prefix here.
Correct. Unlike binary acids, oxyacids just use the anion's root. Let's try 3 examples.
For the first example, we will be using HNO2. The anion is NO2 negative, which is nitrite. Since the suffix is ite, which is ite, we will change it to us. So, the name will be nitrous acid. Now, for the second example, it is also HNO, but it's 3. The anion is NO3 negative, which is nitrate. Since the suffix is 8, we will be changing it to the suffix ic plus acid. So the name will be nitric acid.
For example 3, it's H2CO3. Please pause the video to answer it. For the anion, O3, 2 negative, or carbonate. And since it's 8, change it to ic, which makes the name carbonic acid.
So the trick is ite to us, then acid and ate to ic acid.
Exactly. That's how you know the difference between nitrous acid, or HNO2, and nitric acid, HNO3.
Got it. I won't confuse them anymore.
Perfect. Now you're ready to name any oxyacid.
We've gone through acids. Now let's move to bases.
Bases are usually compounds that contain the hydroxide ion, right?
Exactly. Most strong bases are metal cations combined with OH negative. They are named the same way as ionic compounds, like metal name plus hydroxide.
Oh, so it's just like naming salts, except the anion is always hydroxide.
Yep. Let's go through 3 examples from the table.
For the example number 1, we will be using the sodium plus OH. Now, the cation will be going first, which is the sodium, followed by the anion OH negative, which is hydroxide. Now, when combined, it is just sodium hydroxide.
For example number 2, we have potassium or K and OH. The cation is K positive and the anion is OH negative or hydroxide. And when combined, it's called potassium hydroxide.
Uh, Now let's talk about the rules of balancing chemical equations.
The main rule is that the number of atoms of each element should be the same on both sides of the equation. That's called the law of conservation of mass.
Exactly. We balance by adding coefficients in front of the formulas, not by changing the subscripts.
We should know too that there are exceptions like the diatomic, which are hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine.
Let's try some examples.
Before we review the examples, here are the main rules in balancing chemical equations. First, write the correct chemical formulas for reactants and products. Second, count the number of each element on both sides of the arrow. Third, and or lastly, adjust the coefficients, which are the numbers in front of the chemical formulas, to balance the atom counts. Do not change the subscripts. There is also a mnemonic device we can use to memorize the diatomic atoms, which are hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine, which is have no fear of ice cold beer. Okay? So for the first example, we have hydrogen gas reacts with oxygen gas to form water or H2O. So firstly, we have to list down the elements and how many atoms we have in each element for both reactants and products. So for reactants, for hydrogen, we have 2 and 2 also for oxygen. And for products, we also have 2 for hydrogen and 1 for oxygen. Since for this one, the product side and the reactant side of oxygen aren't balanced, we have to multiply the oxygen on the product side by 2, which also involves hydrogen. So we also multiply hydrogen by 2, which and now we have a balanced amount of atoms for oxygen and 4 for hydrogen, which means that we also have to multiply 2 with hydrogen on the reactant side, making it balanced.